Hello everyone, my name is Gracie. I'm from IT department, A section. My topic is about system effectiveness evaluation using star and delta transformation. Transformation of resistance, star to delta and delta to star. Transformation of resistance is a key tool in solving many problems related to equivalent resistance around a given circuit, etc. It reduces the math work and acts as a bonus while problem solving in competitive exams. In this section, we will understand what are star and delta formations of resistance and also try to identify them in simple circuits. Star and delta formations of resistance is a standard three-phase circuit or network of resistance connected in the same way as their name suggests. The key to solving problems is to identify them in a simple circuit. Star and delta formations of resistance. Star formation of resistance looks like this. Here we can see from the figure, it looks like a star, right? Delta formation of resistance looks like this. From the figure we can see that the delta formation is in the shape of a triangle, right? Delta to star transformation. In this section, we will convert delta formation of resistance to star formation resistance. Here is the formula for transformation. R12 equals to R1 into R2 by R1 plus R2 plus R3. Note that the above formula is cyclic in nature, hence it works the same for R23 and R31. Delta to star transformation. Now let's convert delta to star transformation. Proof. Show that R12 equals to R1 into R2 by R1 plus R2 plus R3. Let's consider the resistance from A to C. RAC equals to R2 in parallel with R1 plus R3. Then RAC equals to R2 into R1 plus R3 by R2 plus R1 plus R3. RAC equals to R12 plus R23. Equating the two, R2 of R1 plus R3 by R2 plus R1 plus R3 equals to R12 plus R23. Similarly, R2 into R2 plus R1 by R3 plus R2 plus R1 equals to R23 plus R31, and R1 into R3 plus R2 by R1 plus R3 plus R2 equals to R31 plus R12. Adding the first two equations and subtracting the middle equations gives R31 plus R12 plus R12 plus R23 minus R23 plus R31 equals to R1 into R3 plus R2 by R1 plus R3 plus R2 plus R2 into R1 plus R3 by R2 plus R1 plus R3 minus R3 into R2 plus R1 by R3 plus R2 plus R1. 2 into R12 equals to 2 into R1 into R2 whole divided by R1 plus R2 plus R3. Therefore, R12 equals to R1 into R2 by R1 plus R2 plus R3. Hence, it is proved. Now let's convert star to delta transform. In this section, we will convert star formation of resistance to delta formation resistance. We will do this by finding equivalent resistance in place of resistance given in the problem. For example, in order to replace R1 and R2, see star formation in the given diagram, we will be their equivalent, that is R12. Hence, here is the formula for transformation. R12 equals to R1 plus R2 plus R1 into R2 by R3. Note that the above formula is cyclic in nature, hence it works the same for R3 and R31. Star to delta transformation. Proof. Prove that R12 equals to R1 plus R2 plus R1 into R2 by R3. This is the same step up as in the previous step up, with the resistors renamed as follows: R12, R23, R22, R13, R32, R12, R232, R1, R132, R2, R122, R3. So the general results of the above proof become R3 equals to R23 into R13 by R1 plus R13 plus R12, and similarly R1 equals to R13 into R12 by R1 plus R12 plus R23, and R2 equals to R12 into R23 by R1 plus R23 plus R13. So R1 equals to R2 plus R1 into R2 by R12, that equals R12 into R23 plus R13 by 2 R23 plus R13 plus R12 plus R13 into R12 into R23 into R12 by R23 into R13. R13 plus R2 plus R1 into R2 by R12 equals to R12 into R23 plus R13 plus R12 by R23 plus R13 plus R12, that equals R1 plus R2 equals to R1 into R2 by R12 equals to R12. Hence it is proved. Find the equivalent resistance in the given circuit diagram in terms of R. From the figure we can see that all the resistance are of R and the voltage is given in V, right? In order to solve this equation, we will transform the circuit and apply the formula side by side. In the first figure, we can see that we have two star formations, right? Let's convert them into delta transformation. After converting them into delta transformation, the resistance becomes 3R, 3R and 3R. Notice the highlighted area in the circuit and then observe the change. Can you identify this transformation? Is it star to delta or delta to star? It is star to delta, right? Next, we will do the same to the other side of the circuit. It will look like this. Then the resistance becomes R2, 3R, 3R, 3R. Now observe. Congratulations, we have transformed a complex looking circuit into a simple circuit we can easily solve. Wasn't that easy? Note that the method shown in this example is not only the way to solve the question. Try transforming other points, make your own way. Overall, Overall answer to the question is 2R by 3. Effectiveness of star delta transformation. The primary side is star connected, hence fewer numbers of turns are required. This makes the connection economical for large high voltage step down power transformers. The neutral available on the primary can be earthen to avoid distortion. The neutral point allows both types of loads, single phase or three phases, to, to be met. Large unbalanced loads can be handled satisfactorily. The YD connection has no problem with third harmonic components due to circulating currents in D. It is also more stable to unbalanced loads since the D partially redistributes any imbalance that occurs. The delta connected winding carries third harmonic current due to which potential of neutral point stabilized. Some saving in cost of insulation is achieved if HV side is star connected, but in practice the HV side is normally connected in delta so that the three phase loads like motors and single phase like lightning loads can be supplied by LV side using three phase 4-wire system. As grounding transformer in power system, mostly grounded Y delta transformer is used for no other purpose than to provide a good ground source in undergrounded delta system. Take for example a distribution system supplied by delta connected power source. If it is required to connect phase to ground loads to the system, a grounding bank is connected to the system as shown in the figure. The system A grounding bank is connected to the system as shown in figure. Note that the connected winding is not connected to any external circuit in figure. With a load current equal to 3 times I, each phase of the grounded winding provides the same current I, with the connected secondary winding of the grounding bank providing the ampere turns required to cancel the ampere turns of the primary winding. Note that the grounding bank does not supply any real power to the load. It is there merely to provide a ground path. All the power required by the load is supplied by two phases of the ungrounded supply. Applications. It is commonly employed for power supply transformers. This type of connection is commonly employed at the substation end of the transmission line. This main use with this connection is to step down the voltage. The neutral available on the primary side is grounded. It can be seen that there is phase difference of 30 degrees between primary and secondary line voltages, commonly used in a step-down transformer. Y connection on the HV side reduces insulation cost. The neutral point on the HV side can be grounded, stable with respect to unbalanced loads, as for example at the end of a transmission line. The neutral of the primary winding is earthened. In the system, line voltage ratio is 1 by root 3 times of transformer turn ratio and secondary voltage lags behind primary voltage by 30 degrees. Also, third harmonic currents flows in the two give a sinusoidal flux. Thank you.